Hello and welcome to section 2.6 rational functions and asymptotes, and in this section we are going to talk about horizontal asymptotes and all the things that go along with them and sketch some graphs. So the first thing we're going to talk about is horizontal asymptotes, and the first one that we need to know is that if the degree of the top and the bottom, so we're talking about the powers here, the powers are the same, then the fraction of the leading coefficients is the horizontal asymptote. Alright, and so we'll talk about that one in just a second, because if you notice the degree of this problem, the leading coefficients are the same. So we are going to, we'll use that, and I'm going to use this on another page. So, and then the other option, there's three options, and you may remember these from Algebra 2. If the degree of the top is higher than the bottom, then the horizontal asymptote doesn't exist. And finally, if the degree of the top is less than the bottom, then the horizontal asymptote is 0. So basically what we're going to be doing is we're going to be using the horizontal asymptotes in order to sketch a graph. So let's go ahead and work on sketching this graph. While we're looking at this, you'll notice that the degree of the top and the bottom are equal, so we're going to use our first one here. And basically what that's saying is if we take the leading coefficients, they're both 1, so that means we have a horizontal asymptote at y equals 1. So I could actually sketch a line, and I'll use this green dotted line as my asymptotes. So horizontal asymptote, that's my first thing that I know for my graph. So I got a horizontal asymptote at 1. Then, well, let's go ahead and find our vertical asymptotes. Well, let's go ahead and see if there's any factors in common, because maybe there's a hole, and that'll also help us get our vertical asymptotes. So I'm going to factor the top. And when I factor the top, it looks like I get x plus 2, x minus 1, and you can go ahead and factor it how you want. You can draw out your x and factor it that way. On the bottom, I'm going to do the same thing, and so I'm going to do x minus 3, and it looks like x plus 2. So you'll notice that right here that the x plus 2's will cancel out, and that means there's a hole in the graph at x equals negative 2. So there's a hole at x equals negative 2 if I set those equal to 0, and the function that agrees everywhere but at that x equals negative 2 point is really x minus 1 over x minus 3. So to get my vertical asymptotes, in this case, if I set the bottom equal to 0, I find out that x equals 3. So I have a vertical asymptote at x equals 3. And so I could draw a line here for my vertical asymptote. There's my vertical asymptote. And then I'm going to have a hole in the graph at x equals negative 2. That's what we found. So somewhere over here. Now I just have to figure out where the graph is going to go. And so what I do is I just pick points around the asymptotes. So I'm going to pick a point, an x and y value that is above the graph. And I'm going to use this simplified function. It just makes my life easier. So if I pick the point, say 2, 2, and plug it in to this function. So I'm picking the point 2, 2. So this point right here, just to see, well, yeah, just to see if the graph actually goes through there. Well, actually, no, I'm picking the x value of 2. Sorry. I'm picking the x value of 2. And so if I get a positive number, then the graph is going to be up here. If I get a negative number, the graph will be down here. And that's just kind of my way. And I know the graph is approaching just because that's the way. That's why we have asymptotes. So I'm going to pick the x value of 2, and when I pick the x value of 2, I plug it in. So if x equals 2 into this function, I end up with 2 minus 1 over 2 minus 3, and you'll see that on top I get 1, on the bottom I get negative 1. So that means that I have negative 1. So at x equals 2, I should be going through this point right here. So that means my graph is going to approach this vertical asymptote from down here, and it's going to approach the horizontal asymptote. But remember, I have a hole at negative 2, so somewhere over here at negative 2, I'm going to have, whoa, if I could draw a straight line, I would have a graph that does something like that. And so just make sure that you have your hole there and in your graph. And if I really wanted to find out where it should be, I could plug in negative 2 into this and see exactly what's happening to get a pretty good idea of where that would be. So then, most likely, then, if I pick a value on the other side of my vertical asymptote, say like 1, 2, 3, 4, I just need to know if I pick x equals 4, then I can find out whether the graph is going to go down over here or it's going to be up in the top up there. so that's what I'm going to check out. So I'm going to pick x equals 4 this time to get the other part of my graph. And this is the way you do it every time. You just say 4 minus 1 over 4 minus 3. And you'll notice that I get 3 over 1, which means when I'm at x equals 4, I'm at positive 3. So the rest of my graph is going to go through that point, and it's going to approach my asymptote. So a sketch of the graph is just kind of a rough estimate of what the graph's going to look like, and that's a pretty good graph of it. If you want to get an exact graph, go ahead and graph this on your graphing calculator to see exactly what's going on there. So then in the next one, we're going to talk about our horizontal asymptotes again, and I'm bringing back the horizontal asymptote summary that I used just a few minutes ago. And so just to kind of remind us of what's going on, and so I'll just kind of put that down here in the corner so we can kind of look and see what's happening with each one of these. So if we want to find just the horizontal asymptotes, we look at the degree, and you'll notice that in this case, in example 5a, the degrees match, so it tells me that I take the leading coefficient, so my horizontal asymptote is going to be y equals 3 over negative 4. And if I can reduce the fraction, I'll reduce the fraction, but I don't need to in this case, and so that's where my horizontal asymptote is. In the next one, if you look, the degrees do not match, so we got to look at it either 2 or 3, and it looks like the top is bigger than the bottom, so when the top is bigger than the bottom, there is no horizontal asymptote. So we could say horizontal asymptote does not exist. And there's another type of asymptote that appears from this, but we're not going to talk about it today. So then, we have the degrees matching, so we look at the leading coefficients. So in this case, the horizontal asymptote is y equals 1 over 1, which is 1. In the next one, the top is bigger than the bottom again, because the bottom is 1. So this one, another horizontal asymptote, does not exist. And then finally, you'll notice that the top is smaller than the bottom, so the horizontal asymptote, by looking at number 3, when the top is smaller than the bottom, we have a horizontal asymptote at y equals 0. And I shouldn't have put an equal sign there. It should have been like a colon or something like that. So that's really what we're talking about when we're doing these, and so that's how you can quickly identify the horizontal asymptotes. It doesn't matter what the leading coefficients are when the degrees do not match. It only matters when the degrees match. So our final example here is talking about sensitive skin and exposure to the sun. And so we're going to go through, and basically in A, we're going to find out the amount of time that you can be exposed to the sun when you have very sensitive skin. So basically, they're telling us that at the time, or S, so a person's sensitive skin in time. So we're trying to figure out how much time they can be out there without burning. And so basically we have this S, which is our sun sensor scale on how strong the intensity of the UVB rays are. And so we want to find the amount of time a person with sensitive skin can be exposed to the sun with minimal burning when we're at a sun sensor scale of 10, 25, and 100. So in order to do a problem like this, we have to figure out our time. We're just going to plug in these numbers. So we say 0.37 times 10 plus 23.8 all divided by 10. And so that would give us the time if this scale was at 10. If we want to figure out at 25, we would do the same thing. So t would equal 0.37 times 25 plus 23.8 all divided by 25. And I guess we should probably figure out what these numbers are. So if you get out your calculator and actually plug these numbers in, you will find out that you get approximately 2.75 hours for that one, for when the sun sensor scale is 10. When it is 25, you will end up with, you only get an hour and 30 hour 0.32. So you're talking approximately an hour and like 15-20 minutes, something like that. And then finally, when it's at the top of the scale, you take 0.37 times 100 plus 23.8 all over 100. When you're at the top of the scale, or pretty close to the top of the scale, because you notice the scale goes from 0 to 120, and so when I do that, you get approximately 2/3 of an hour, which isn't very long. And so then that's basically what we're talking about. So you can see as the sensor scale goes up, how much time do we get for you to be out there? Well, it's going to be a lot less time. So if this is a valid model, what would be the horizontal asymptote of this function, and what would it represent? Okay, well, looking up here at our function, you'll notice that the degrees of our function match. So that would mean that we'd take the leading coefficients and divide them. So our horizontal asymptote for this one is going to be y equals 0.37 over 1, but I'm not going to write it over 1 because there's no need to do that, because 0.37 is a good representation of this. And basically, what does this mean for us? This means that this is the minimal amount of time that when we're at the highest scale, this is the minimal amount of time that you can spend out in the sun. So we're talking 0.37 hours would be the minimal amount of time that you could spend out in the sun before you started burning at the top of the scale. And so this is basically what horizontal asymptotes do for us. Horizontal asymptotes give us end behavior of a function. It doesn't necessarily give us what's happening to the function everywhere. It just gives us how does the function, what happens to the function as you go out to an infinite amount of time. So thank you, and if you have any questions about this, please come to class with them.